So, welcome everyone. My name is Danny. I'm a second year PhD student at the University of Salford. My research focuses on enzymes. And the big goal is to find ways to replace some of the chemicals we currently pull out of oil by using waste. But before I get into all of this, as it's the weekend, I'd like you to think. A pint of beer. Every pint brewed leaves something behind. Not just good memories, but actually a physical byproduct. And it is that I intend to use. My research is about changing that waste. Now, a request before I get going. Can everybody please get their phones out? I will be asking you to scan a QR code, so please have it handy. Why is this research important? Well, every industry that you can think of relies on oil at some part. Be it the food we eat, the clothes we wear, the buildings that we live in. They all rely on chemistry that, in essence, comes from oil. It's deeply embedded in our modern lives. It's not just fuel. Bio-based alternatives have the potential to replace many of these chemicals. The raw material, plant waste. Without drilling another barrel, without depleting something we can never, ever get back. That's the bigger picture that my research fits into. So, this chart shows crude oil prices over the past 20 years. The first thing you'll notice is how volatile it actually is. In less than 20 years, it's swung from $150 a barrel to almost zero, and then back up to where it is now. Each one of these swings has happened due to instability, be it a handful of countries making political decisions, a war, a global pandemic. Each decision has changed our lives. It matters to every single person in this room. Not just because of fuel, because of plastics, fertilizers, pharmaceuticals, things we rely on. That is why finding alternatives, like bio-based chemicals, aren't just a simple decision of if we can, it's more when. It's not just about the supply, however. It's not just about the price, it's about the supply. Go ahead and scan that QR code behind me. It'll take you to a website that is showing you the live estimate of oil, how many barrels we have left. At current consumption rates, we have around 47 years of oil left. That's within most of our lifetimes. We're currently burning through 102 million barrels a day. So we need to find those alternatives. And for those of you with a live figure, this is how many barrels were left when I did this PowerPoint. Compare those two figures. That difference is something that's really worth sitting with. So what am I working with? When you brew beer, the two main ingredients, other than the obvious water and yeast, are hops and barley. Barley provides the sugars that ferment into alcohol, and hops provides bitterness and an aroma. But once that brewing's done, where does it go? Well, oftentimes it's thrown away or given away as plant food, as animal food. Now that plant material, when used as animal feed, actually is only able to make up about 25% of that replacement for regular animal food. Locked inside of that waste, however, is things that are valuable to us: hemicellulose, cellulose, and lignin. But how much am I looking at? Well, I need to understand this problem. University of Salford is really unique. We have our own brewery. So using data from there, I was able to work out that the UK brewing industry uses about 94 million metric tons of brewing spent grains every single year. Now that's a big figure, really hard to imagine. But what I'd like you to think is that's the equivalent to one African bull elephant every 2 seconds. That's a lot. So going from the large to the small. If we look at our spent grain, we look really closely, we magnify them. We're able to see plant cells. Going a little further, we have our plant cell wall. It's made up of 3 polymers, 3 fibrous structures: lignin, hemicellulose, and cellulose. They make up about 73% of the overall structure. But they're tightly wound together and they need to be processed for them to be useful for industry. How am I going to do that? Okay. I'm going to use a solvent. Now, we've all come across solvents. They break things apart. For those of you that have ever used nail polish remover, acetone, that's able to break down that dry nail polish, break it apart. Simply, that's what I'm going to be using, an ionic solvent. That's able to break apart these 3 fibrous structures, making them available for enzymes to break down further, making them into valuable products. But what is an enzyme? Well, an enzyme, think of it like molecular scissors. But unlike scissors, it's incredibly targeted, very precise. It only cuts where you want it to cut, making that a truly clean and sustainable process. The really clever part, however, is that enzymes are reusable. They don't just wear out. So I can use it over and over again. So, here's where it gets really exciting. That fibrous structure, that chain of polymers, think of it a little bit like a string of beads. Where you break that string of beads changes the product at the end. Break it in one place, you get one chemical. Break it in another, you get another chemical. For me as a researcher, that gives me lots of options. For industry, potential. The real beauty, however, is the use of enzymes. They're clean, they're precise, no mess, no unwanted side products. That means an unchanged product for industry. Now, I need to be honest with you. I'm not the first person to be doing this, but the present methods are expensive. They either require a lot of heat, a lot of mechanical input, which is expensive, or very strong acids or alkalis, strong chemicals that are environmentally damaging. You're either paying a lot or you're damaging the environment. My process is cleaner, simpler, less expensive. Value at every single point. How am I actually going to do this? Well, I've discussed a solvent. But I need enzymes. Where am I going to search for them? Where do you find these? Mother Nature. Nature has spent millions of years evolving to find ways to break down these strong fibrous structures. As a researcher, I search publicly available databases. Of the millions that have been described out there, very few have actually been researched. It's a difficult job and normally takes a very long time. Until recently. So, if you look on the left, that is a 3D structure of a polymer. An enzyme. Pardon me. that 3D structure actually denotes how that enzyme works, how it's able to fit. Think of it like Lego blocks. They fit together with only one type of thing. AlphaFold 2 is able to simulate these structures quickly, cleanly. What would normally take a year to produce just that simple structure actually is able to be done in minutes. Using that, I can use other software to model these processes. Now, this might not seem like a big deal to you, but how important this is denoted by the fact that the team behind this gained the Nobel Prize in Chemistry in 2024. This allows me to process millions of enzymes, or potentially millions of enzymes, in a very short period of time. Now, I've discussed the computer side of things. I'm actually running 2 phases at the same time. Over a 3-year period, I have my lab work, the computational, and then the scale-up. So my 2 phases at the moment, I have the computational, and I have this. I'm growing mushrooms on spent grain. I'm growing 6 species of mushrooms that ordinarily will not grow on grain. This forces them to create enzymes that actually break down that grain. Give me access to enzymes that wouldn't be normally seen in nature. The 2 tracks, the computational and this biological track, feed into each other. The advantage of doing this is the mushrooms I'm growing are edible. They're saleable. And are being sold by the university to help fund part of my project. Research is expensive. I don't have that deep a pocket. So, I have my enzymes. I have my process, I have my targets. What do I do next? I need to test them on first artificial substrates, so in the lab, then on the spent grain. Then I step up from there to make it available for industry. To sum up, the big picture. The problem is we depend on oil for far too much. Fuel, plastics, medicines, chemicals. It's going to run out. Breweries are generating millions of tons of spent grain every single year, and it just gets thrown away. The approach, use a solvent to break that down, enzymes to break it down further, to produce industrial chemicals. Harvest those chemicals. The goal, produce industrial chemicals from what is currently waste, reduce our dependency on oil, that instability that is affecting every single one of our lives. Turn disposal problem into a sustainable resource. Simply, bare waste, ionic solvent, enzymes, industrial chemicals. Truly is that simple. Now, this is an ongoing process, an ongoing piece of research. Hopefully, TED will invite me back to do a talk when I've completed. But for now, thank you all for attending my TED Talk.